Okay, and we're live. Hi guys, welcome to another live stream. This is the third one now, and this time we will be looking at VCAs because I've been thinking about the topic, and just after making the diode ladder filter, I had like a rough idea of what I wanted to try, and so I have some sort of concept. I have not yet really tried it, so this will be a bit risky because it might not really work all that well in the end, but I do think that we might be able to get something useful out of it. Okay, so if you could please confirm that you can hear me and that you can see everything, that would be great. But as always, I will just pretend that you can see and hear, and I will just go on. Okay, so first of all, I guess the question is warranted. What are VCAs? Because not everybody might know. So if you compare a filter to a VCA, then I would say the only difference really is that a filter will remove the volume only of certain frequencies. A VCA will remove or increase the volume of the whole frequency spectrum at once. So it's basically just like a volume knob that you can control with the voltage. So the idea is really just what we're trying to do today is we want to build something on the breadboard that we can send some sort of audio signal in, an oscillator or anything else, and then we can send in also a voltage, and this voltage should be able to control the volume or the amplitude of the signal we send in. So that's kind of the goal today. And I would say let's just start out. So I will switch over to the simulator. And for everyone who's new, like if you don't know, this is basically just a circuit simulator that runs in the browser. You can find it under this address. The page is called Falstad. The tool itself is called circuit.js, and you can find it in different spots on the internet, but this is the page that I usually use. And what's happening here is you can basically build any circuit that you want. Like, it has most, if not all, of the components that you might need. And then what you can do is you can simulate the circuit. Now, of course, all the professionals are going to tell you this is not, like, this will often lie to you or be inaccurate. So you shouldn't take everything you see here for face value. So it's not always going to be like one-to-one the same as it would be if you build it on the breadboard. But still, I think this is actually super, super useful. If only you are, you're thinking of a new circuit idea, something, and you want to try it out. And I think it's just so much more convenient than putting it together on the breadboard, troubleshooting, then it doesn't work. Then you spend hours, trying to figure out why it doesn't work. And yeah, so that's why I like to use this this simulator. And one more thing that I'm going to say right away, my streaming software does not show you my cursor, unfortunately, in the simulator. So what I will try to remember to do is I will try to, just drag, because then you can see, whatever I'm dragging on, and I will try to highlight whatever I'm talking about like this. And I hope this will work for you guys. Okay, so like I said in the beginning, for me it's like it's very useful to think of VCAs in relation to filters. And if you think back like to the very basics of how a filter works, then you might remember that really like the most basic of filters is just this. It's just a resistor followed by a capacitor to ground. That's all. And then what happens is, you can see here and here, you have some sort of input signal. I always like to use square waves here because it's like the most obvious what happens to it with the filter. And what we do is we take this square wave and we push it through this resistor, and then this causes the capacitor here to be charged and discharged. And you can see this here nicely, like the yellow dots are basically the current that's flowing. So whenever the square wave here is in its high phase, that's whenever this turns green, then it pushes the current along this line through the resistor and into the capacitor. And whenever the square wave swings low, then this goes red, and you can see that the current is basically being sucked up from ground and into the capacitor. And so the capacitor basically discharges into the source again. And as you might remember, if you've seen some of my videos, I like to compare capacitors to balloons that you push water into or pull it out of, because then you can kind of imagine that you have here like a kind of narrow sort of pipe which you push water through. And because, I mean, 100k ohms is quite a lot of resistance, so this pipe would be like really narrow. And so what happens is, whenever the oscillation here goes high, it pushes just a small amount of water through this pipe. And so it takes a bit of time to kind of charge this capacitor up. And you can see this down here in the graph. Like you can see, like whenever it goes high, you know, it takes a while until it's completely at the top level. And then it also takes a while until it's at the bottom again. And I can increase this effect if I, for example, increase the value of the capacitor, which means, you know, the balloon is bigger, so it takes longer to fill it up and drain it. And you can see, you know, now it takes like really like a lot longer to fill it up and to drain it. And you can also see that it doesn't get all the way to the top even, because, you know, in the time that the wave is in its high phase, it's not long enough to fill the capacitor up completely. So that's already interesting. But enough about filters. This is not what we're here to talk about today. And what we are here to talk about is VCAs, so amplitude control. And if you take this kind of circuit that I have here, this kind of basic filter, and you ask yourself, okay, what do I need to change to turn this from a filter into some sort of amplitude control circuit? And that is actually very easy. Like you just take this capacitor and you replace it with a resistor. Now, why does this work? Well, it's actually quite simple. So like the easiest explanation that I can think of that makes sense is, or maybe it's not that easy, but for me it's easy. So the idea here would be, you can also think of the capacitor here as a resistor that resists only certain frequencies. So only like very low frequencies are able to pass through here, and no, other way around. Very fast frequencies are allowed to pass through here, and very low frequencies are kind of filtered out. That's kind of the idea here. And a resistor treats all frequencies equally. So a capacitor is kind of selective in which frequencies it lets pass through it, and a resistor will say, oh, it doesn't matter, like everything can go through. And so what happens here basically is that you have your signal, again, that's swinging from high to low, and it's pushing, like I said, water through this narrow pipe into this area. And then what happens is there is another straight connection to ground, or there is a straight connection to ground through another narrow pipe here. Now this pipe is less narrow than the other pipe. And so what happens is that the water can basically leave, or, you know, just escape through this connection and flow straight to ground. But not all of it at the same time. And so some of it will be kind of retained at this point. And this means that we do have a voltage here, like we don't have zero, like we have some voltage, but it's going to be less than the voltage that we have here. And I can show you this if we make this resistor here variable. And let's say we can go from 0, so it's just a straight connection, to something like, let's go with 100k. Okay, And now I can use this slider to control the value of this resistor, basically. And so what happens is, if I increase the value of this resistor, then you can see down here that the waveform gets bigger, which means that the amplitude gets larger. Because if you see a waveform on an oscilloscope like this, the relationship between the size and the volume is basically 1-to-1. So an increase in size means an equal increase in volume. And so as I increase the value of this resistor here, the signal gets louder. And vice versa. So if I decrease it, let me bump up the speed here. Okay. So if I decrease the value of this resistance, the oscillation gets smaller and smaller. And we can't go to 0. Okay, but now we're at 1K, 100K, and the signal is only swinging between plus and minus 50 millivolts. And now, if we just put in a straight connection to ground, then we have nothing. Because you can imagine, or I like to imagine it this way, that all the water that's passing through the resistor here doesn't hang around here, like it just goes straight into ground, or gets sucked up from ground. So there's no pressure or voltage at this point, so we have 0, so nothing. But if we go back to this and we have a resistor here, then you can see that we do have a voltage here, even if it's very, very small, but we do have a voltage here. Okay, and you can see now by controlling the resistor value here, I can control the amplitude, which is basically what we want to have in the end. Like a VCA would just be a device that can basically do this. So we send in a signal and we have some sort of control element here, and we can control the amplitude of the signal. So far, so easy. Okay, let me check the chat for a second to see if anything's going on. Oh yeah, I'm using English labels. Yeah, I switched it. I realized it's a bit jarring if it's in German. Okay. If you increase but keep the resistor ratio the same, what happens? Nothing, Ethan. If you keep the ratio the same, so if you go 1 mega ohm here, oh no, that's not right. If you go 1 mega ohm here, and now you go 520K, it's exactly the same. So this doesn't matter. I mean, the only thing that changes now is the amount of current that's flowing through these resistors, but just for the amplitude, so just for the voltage, it doesn't make a difference. Though in general, there's one thing that is kind of can be a problem here. If you use very big resistors, they can introduce noise. It's called Johnson noise. It's basically the noise that a resistor makes, for lack of a better explanation. And the bigger the resistor, the more noise it introduces. So that's why you don't always use like mega big resistors all the time, basically. Okay. Then let's go on. Okay, so as you might have deducted from what I just explained, another important thing is that it doesn't matter which resistance we vary here. So right now we changed this one, and this caused our amplitude to be changed. But we can also just change the resistance of this resistor. So if I decrease this, then the voltage here increases, because, I mean, it makes sense, because now more water can pass through here, so more kind of hangs around here, so our amplitude goes up, and like this it goes down. But you will notice that the kind of relation is inverted, so we would have to increase the value here beyond 100K to actually reduce the amplitude. So now if I increase the resistance here, you can see that the volume goes down. But in the end, you know, it doesn't really matter which one we pick, which one we want to change. They will both have an effect on the volume. Okay, and as stupid as it might sound, basically this is all there is to a VCA. So this is a VCA if you find a way to control one of these two resistances with a voltage. And this is basically, I mean, when you look up VCA designs, like popular, you know, DIY VCA designs, what you are going to find are VCAs that use operational transconductance amplifiers, so OTAs. Mostly it's going to be the LM13700 chip. And if you look at the schematic, maybe I can find it. Let me see. Okay, this one is from the datasheet, I think. Yeah, I mean, let me see if I can get this a bit bigger. Okay, hope you can see this. Let me check the chat. You can also say a capacitor resist changes in voltage. True. It's a basic voltage divider you've drawn there, is it not? Yes, it's just a voltage divider, that's all. Very, very simple. Big in physical size or value? As far as I know, value. So physical size is only relevant, I think, for like how much current it can handle, like how much heat it can dissipate. Attenuators are a completely different circuit, or I think normally the distinction that you would make is that an attenuator is passive and a VCA would be an active circuit, you know, voltage controlled amplifier. So you at least would expect a VCA to have a low output impedance. So it should be able to provide a lot of current. And an attenuator, like you can just use a potentiometer, for example, but that would be passive. So it can't supply a lot of current usually. Okay, depends on how big the Johnson is. Yeah, exactly. Okay, so let's get back to the OTA circuit. So if you've never seen an OTA, then this might look quite daunting and complex. But in the end, this might sound crazy, but in the end, this is just a voltage divider. This is just what I've shown you here. But what they do is they replace this resistor here with the OTA. And then the OTA, you can control it with a current. And this current will basically, it's not one-to-one applicable, but in this scenario, you can kind of think of the OTA as a voltage-controlled resistor. And then what you do is you feed it a current, and the more current you feed it, the more it kind of lets the input signal come through. And then here you have the other, like this is the resistor that you see here basically. So this one, I mean, it's a 30K here, but it serves the same purpose. And then this is a buffer, and then here is output, and that's it. But I mean, in general, this is all that is. So simple. But I don't want to do this. Like I don't want to use an OTA. Basically for two reasons. The first one is because it's boring. I mean, I might do a video on OTAs at some point, but for now, not that interested in it. And the second reason is OTAs are kind of expensive, so, like compared to other chips. I haven't looked it up I haven't looked it up recently, but I think in my local shop, like an LM13700 is like around like €3, €4, and compared to other chips, that's really a lot of money. And so what I would rather do is I would rather do a kind of simpler, like with easier to get components layout. And as most of you know by now, I'm currently really into diodes. So what we're going to do is we are going to use just very simple diodes. Okay, I will check the chat if anyone has any questions. What you showed is attenuator amplifier. Yes, true. Like you know, what I show in the simulation is just a voltage divider, so it is an attenuator. So we will need amplification, but we will do that. Really, what you need from VCA and synth is voltage control volume. True. You can simulate. Yeah, you could. If I would go with the OTA route, I would simulate it. But right now, I'm not going to do that. So, so the question is, how are we going to use diodes to make a VCA? Well, it's basically, it is very, very similar to the concept that I used for my filter. But since it's a VCA, we're going to have a little bit of an easier time. We're going to use up less components. And my goal for this is basically like I want to have a design that only uses one TL074, so only one op-amp chip. And I don't want to use any ICs besides that. And yeah, I want to use like as little components as possible. And you know, to be able to have the circuit be as compact as possible. And you will see that this comes with a few trade-offs, but we will try to kind of navigate them and get something that is at least usable. Okay, so I will delete all of this stuff, and I will quickly draw you up the idea that I have, and it's just going to be like the first outline of what it's going to look like. Okay, so what I like to do for this kind of stuff is I like to use a triangle wave as an input, simply because like with sine waves, for me it's a bit hard to spot distortions. With a triangle wave, I think it's very obvious. Like whenever you start to get any non-linearities, you can clearly see like how the shape is bent. And then you know, okay, I have to back off. I have to do something else now. Okay, but we'll start out with a triangle wave. We will make it a bit faster, and then we will put this on our scope. Whoops! I have to change the settings here. We're only interested in voltage for now. Let's turn on the speed. Okay, so this is our input triangle. Okay, so let me draw up the basic concept. This resistor is basically in the same orientation. It's the same thing that you just saw from the voltage divider. So we are going to pass our oscillation through this 1 mega ohm resistor. And then what we will do is we will use a diode here, and we will use a diode here, and we will get our output from here. And right now it's just going to be our triangle wave, naturally, because I mean they are not connected to anything, so it just passes through them and there's nothing affecting them. Okay, but then what we do is we will use a voltage here, and we will use a voltage here. And the basic idea is, if we now take, wait, I have to stop the simulation, otherwise it's going to scream. If we take a really small voltage, so we take 400 millivolts here, we take the opposite, so the inverse of that here, so it's minus 400 millivolts. Oh, then it just dies. Oh, it's minus 400 volts. Yeah, that won't work. Cool. Reset it. Okay. Turn on the speed a bit. Okay, as you can see, we have something interesting here. So on the left-hand side, you see the original oscillation. It's 5 volts peak to peak. So the upper spike is 5 volts, and the lower spike, you can see here, is minus 5 volts. And just by doing this, we were able to reduce the volume of our oscillation down to just you can see that the top value here is 330 microvolts. So it's already really quiet. Oh, one thing. This I always fall into this trap. The like one problem with this simulation for me is that whenever you draw in a diode, so you just select diode and you just draw one in, it will give you the default model. And I'm not sure what that is supposed to be, but it is behaving very different from a 1N4148. Like these are the ones that I generally use. And this default thing, I don't know what that actually is, but it has very different properties from this one. So I always have to go here and I have to switch that in. And then the circuit's going to behave differently. Yeah, you can see that now the output signal is quite a lot louder. It's now at 8 millivolts instead of, what was it, like 300 microvolts. And the reason for that is basically that these diodes they resist the current a bit more, so there's less current going down this route. Okay, but before we kind of explain what's going on here, let me just switch around or switch these values up here and down here around a bit. So right now we're at 400 millivolts and the signal is really quiet. So let's see what happens if we go down to just 0 volts. Okay, and here you can see what I meant earlier. So this is obviously not a triangle wave anymore. It's not even close. It actually looks more like a kind of freakish sine wave. But you can just tell that the triangle wave is being distorted. So this is not our triangle. Now the question is, why is it being distorted? And I think I can actually show you. Yes. Okay, so I really bumped up the current speed here, so you can see what's kind of happening. Let me slow it down a bit. Okay, so we have 0 volts up here. We have 0 volts up here. So ideally, these diodes should not be, like, there should not be a current flowing through these diodes because there's no voltage difference between top and bottom. But the problem basically is that this signal, I mean, remember, like, this signal is swinging between plus and minus 5 volts. And so what's happening is that the signal is strong enough to kind of activate the diodes and either suck in current or pull current down here. You know? So whenever the wave is in its low phase, it's going to suck current in, from ground here through the resistor and into the signal. And whenever it's in its high phase, it's going to push current through this resistor and down to ground here. And this will definitely distort the voltage here because you can see that where this should normally be a straight line going to the top, you now have this kind of curved and bent shape. And this is because the signal here is so strong that it kind of is able to activate the diodes. That's the problem here. So what's the solution? Very simple. We simply just turn down the voltage of this. So let's first go down to 1 volt and see what happens. Okay, this is still very distorted. So we know, okay, 1 volt is still enough to activate the diodes and have them distort the sound. So what happens if we drop it down even further? Let's go down to 750 millivolts. Not that much better. We drop it down to 500 millivolts. Now it's getting a bit more triangle-ish, I would say. Like a bit more pointy at the top, but still not good enough. So we drop it down to 300 millivolts. That's even better. And we go down all the way to 100 millivolts. And then we might zoom in a bit. Yes. This looks much better, I would say. So let's also zoom in here. Yeah, I mean, probably there's still a bit of distortion in there. We could go even lower here. Try that. but now it looks like pretty much undistorted. So I would say 100 millivolts peak to peak is probably where it's at. I mean, it also depends on what you like. Like you could also experiment with having a stronger input signal going in, so that, you know, maybe you want to distort the sound a little bit. We can also try this later. But yeah, now we can see that when the diodes are both set to 0 volts, then we have roughly the same amplitude here as we have here. So here we have 50 millivolts or 100 millivolts peak to peak, and here we have something like, what's that, 82? But yeah, so we basically have like a 1-to-1 transfer from here to here. And now, if we increase the voltage up here, and we accordingly decrease it over here, then we can see that we have, I mean, because I selected this max scale option, you don't see it in the size of the actual display here, but you can read it here. Like you can see you have 50 millivolts peak here and minus 50 millivolts valley here. And then on this side, you just have a 20 millivolts peak and a minus 20 millivolts valley, basically. And as we increase the voltage here and we decrease it over here, we can see that the effect will only get stronger. Like now you have, like again, 100 millivolts peak to peak here, so 50 millivolts minus 50 millivolts, and over here we now have just 4.45 positive and minus the same negative. So what we can see is, as we increase the voltage difference between this point and this point, the amplitude of the signal, here, or at the output rather, is decreasing. And this is basically what I want to exploit for this idea. And I will check back in the chat to see if you have some questions. Let me see. There's a more synth-specific chip for dual VCA as well. Yeah, true. There are, like, from this kind of line, there are a bunch of chips that do synth-specific things. There's also an oscillator that's just fully featured. It's just the chip, and you can totally use them. But for me, it's not really fun because it's already done. It's like buying a plugin. It's perfectly fine, but for me, it's a bit. It's not that exciting. Viewing in frequency domain should allow one shared view of gain along with nonlinear distortion. Not sure what you mean, Christopher. You would have to reiterate. If it's nonlinear, then there won't be static frequency domain response. What kind of diodes are those? 4148. Yeah, right. What do you mean by static? For a given tone at a given amplitude, you will get a deterministic set of harmonics according to the characteristics of the diode. Not sure what you mean. Many p-n junction diodes will perform similarly, but these are really common and cheap. Yeah, okay, so let's just go on. And we will see how it sounds in the end. Okay, so back to the basic concept that I was describing. So, I mean, this is basically all there is. What we will need to do, as some have pointed out before, is we will need to amplify the signal. Because, as we've seen, if I drop this again down to 0 volts, and I drop this thing here down to 0 volts as well, then the signal here is very quiet. I mean, because, of course, like the input signal is very quiet, it's only 50 millivolts, or 100 millivolts peak to peak, so naturally the signal here is also going to be really quiet. So what we will have to do is we will have to amplify the signal that's coming from this point, basically. And the way we'll do this is very easy. We will just be using an op-amp. And we will, no, that's the wrong orientation. I don't like that orientation. So let's just go with this one here. Boom. Okay, So all we have to do is we have to connect this point to the non-inverting input of our op-amp. And then what we do is we set this up. Oh no, actually the other orientation was actually better. Okay, I'm very sorry. Please have patience. So this one is better. Okay, so connect this point to our op-amp, and then I will put this thing here. I will pick a rather big resistor value here. I will pick a rather small resistor value here. And just if you don't know, this kind of setup it's basically the same as when you use an op-amp as a non-inverting buffer. But by using a voltage divider here, you can kind of handicap it. So what the op-amp, like this is very simplistic, but what the op-amp will do when you set it up like this is it will try to match the voltages here and here. So it will push out current or pull in current to try and get the potential here the same as there. And if you don't have any form of voltage divider here, if you just have a straight up connection, then it will just follow the voltage that you have here. But if you put a voltage divider right here, then you will kind of make it harder for the op-amp to balance these 2 points, and therefore you force it to work harder. And that's all you do with this. And so what we can do now is we can put our output here, and magically we can see that even though we only have a 50 millivolts input here, we get a 4.21 volts, or like 8.8 something volts peak to peak output. Now, one thing that might be tricky here or of concern is, of course, that since our input signal is like pretty quiet, this is kind of susceptible to being noisy, of course, because you take a quite quiet signal and you inflate it by a lot. So naturally, like any kind of noise that you have at this point is going to get amplified along with the signal itself. So that's why, you know, you should maybe try to push this up like as far as possible without the signal getting distorted. So what I was thinking is we might just try it with the 100 millivolts input and just see, you know, how it sounds, how it's going to turn out, because then we can actually drop we can raise the resistance here a bit, and thereby kind of not make the op-amp, you know, work just that hard and possibly blow up noise that much. But I mean, in the end, like when I was working on the filter, I was kind of concerned that the noise might be very prominent. But and to be fair, like as long as I had the circuit on the breadboard, there was like a fair amount of noise. But then when I made the PCBs and you know, I constructed the PCBs and I built the module, and I checked that, it was actually I couldn't really hear much noise, so it was really like negligible. The problem is just that breadboards, in my experience, are generally just very noisy. And I think last time we kind of, like, people were kind of discussing this and giving some insight into why that is. But yeah, just my experience, breadboards are very noisy. So that's why when we built this, probably it's also going to have some noise, but that's not necessarily because of the way the circuit is constructed, just as a heads up. And one more thing, I don't want to confuse you, but what you can also totally do, what I've tried is, if you use multiple diodes here, you can kind of push the point further as to when the input will be distorted. But we can look at this maybe in the end when we try to tweak this circuit, basically. Okay, let me check the questions again. what's the purpose for the op-amp working harder? The op-amp is just blowing the signal up again to be loud enough, you know, because if we just took the input signal, which right now is just 100 millivolts peak to peak, if we just take that and amplify it, it's not very loud. That's a problem. Should you match the diodes when you build it so you get less distortion because of different forward voltages? Probably you should. I mean, for my filter, I have tried to match them. I did match them. I couldn't tell that much of a difference in the end. So, I mean, your mileage may vary. You should probably just try it. But for me, so far, just using random diodes I have laying around was working okay. Maybe also depends on how much of an audiophile you are, so how sensitive you are to imperfections in the sound. Okay. Can you explain the theory behind when the current gets sucked in from the source, the effect it has on the voltage when you apply the diodes? Yes. That is what I'm going to do now. And Pitovsky, no, we are not going to use an OTA. We're going to use diodes. Okay. So let me explain what exactly is happening here. So for now, we'll take this thing away again because I think it's a bit distracting. Okay, so let's just look at this structure here and try to find out what's happening. So if I increase the current speed, okay, this is like really at the maximum. So you see here that there is some current flowing through the diodes, but it's just like a very tiny amount, and that's why you might have some distortion, but I think it's rather negligible. But okay, so for all intents and purposes, what we can say, what is happening is that if we put a load here, if we put a resistor here, then yes, then we can see that there is something happening. So we can see that the oscillation, like the very small oscillation that we have, is pushing and pulling current through this resistor to ground and up from ground. So whenever the oscillation is in its high phase, current flows through here and to here. Oh, you can't see, right. So whenever the oscillation is in its high phase, current is flowing from sorry, it's flowing from here through this resistor, and then down to ground. And the other way around when it's in slow phase. And because we have 0 volts up here, we have 0 volts up here, the diodes are basically not active. That's how you can think of it for now. So they are basically, they look like there's no connection here. So our oscillation is not passing through the diodes basically, which is why we get mostly, you know, like with all of these things, it's never absolute, but we get mostly the same oscillation here that we have here. So it's going to be just transmitted because, yeah, again, it's as if these diodes were not there because they don't conduct at the moment. But as soon as we increase the voltage here, and I'm going to do it like very drastically now. So I'm going to go 400 millivolts and minus 400 millivolts. So then what you can see is that you have a constant current that's going from, you have a constant current that's going from here through this diode, through that diode, and then down to the minus 400 millivolts. So it's just like, you know, like a constant river that's basically flowing through here. And this is not scientifically accurate, and just as a disclaimer, I'm really not an engineer, but the way that I think of it is, it's kind of as if there's like a big river flowing here, and then you have this other signal that's trying to cross the river. But because the river is like so powerful right now, like there's so much water flowing down the river, most of your signal, like most of what you're going to push through here, or, you know, back, you're trying to suck back in here, are just going to go into the river or come out of the river, you know. So it's just flowing from here to here and from here to here, and that's why we don't get much of a signal over here, you know, because I would have to kind of turn this down so you can see it better. Yeah, I mean, it's again, it's all just approximations, but now you can kind of see that, now you can't really, let me try to get this a bit better. Maybe if we raise the resistance here a bit. Yes, okay, because a 1K load would actually be kind of a lot. Now you can see it much better. Okay, so now you can see that whenever the oscillation here is pulling, it's pulling water out of the river, and whenever it's pushing water into the river, basically. And the water is never going to arrive over here, because it's all swallowed by this like very fast moving river. Sorry, metaphors are all over the place, but I hope this kind of helps. Let me check again. The cursor doesn't appear when you share. Yeah, it's a problem. I will try later with the whole screen. I hope it works for now. If I just drag it and mark stuff. 0 volts on the diodes means ground. 0 volts always means ground. Ground and 0 volts are the same thing, basically. Okay. So hope this is kind of clear. So this is what we're doing. We are increasing the amount of current that is flowing through this path, and by this we're kind of killing the signal. And whenever we turn this down, so whenever we have 0 volts going through here, then no, this is too big. But now you can see that the oscillation is getting here, because there's no river that it has to cross. It's going to suck it away, so it can just like happily pass through this kind of junction point, and then we get our signal at the end. Okay, so let's get back to the amplification part. So we will take our op amp here. We will put it in here, and like I said earlier, so right now we have a very quiet signal here. It's just 200 millivolts peak to peak. We pass it through our junction point here, and then our op amp is basically just looking at it, and it is basically then blowing it up. So it is amplifying it by a lot, and then we get here an 8 volts peak to peak signal at the output. Now probably this is I don't know, it depends on the application. Probably it's going to be too loud. In my case, actually I don't know how it's usually done, but in my case, for my modular, the VCA is kind of is often the final point. It's like where the signal comes out. Maybe you feed it into some effects thing or a mixer after that. But yeah, I mean, it's a question. Like, do you want to have a 5 volts peak to peak signal at the output, or can it be quieter? I don't know. I think it doesn't really matter at the moment, but I mean, you would have to just adjust the resistor values here to get the volume level that you need for your application. Okay, so this is the basic setup that we're going to work with. Now we have to kind of answer 3 questions. First question is, how do we get the voltage up here? Which should be quite easy, because it's just, it's just a control voltage that we apply. But then we also need to get the inverse of our control voltage to apply to the bottom here, because like I showed you, we always need to have the inverse of the voltage up here down here. So if we have 500 millivolts up here, we need to have minus 500 millivolts down here, and that applies for every other voltage that we apply. So the question is like how, like ideally with a VCA, you would just apply, like a single CV, you would just apply, say 1 volt, 2 volts, 3 volts, whatever, and you expect the VCA to react to that control voltage in an increase in volume. So what we're going to need to do is we're going to need to create an inverted copy of our control voltage in the end. So that's the first 2 questions, and the third question is actually the easiest. how are we going to get our signal down to the 200 millivolts peak to peak that I have applied here right now. And I would suggest that we start with that because, you know, like I said, it's the easiest. So what I will do is I will take this signal here and I will blow it up again, or I'll reset it to what it was initially, which is a 5 volts peak to peak signal, which in the modular world is like, it's kind of a standard that you use. It's 5 volts peak to peak. So whenever I kind of try to design a circuit, a module, whatever, I'm going to assume that that is going to be the input signal, 5 volts peak to peak. So that's why I choose this here. Okay. So then what we're going to do is, the first rule, like what you always should do, is you should use AC coupling. I've explained this in a few of my videos. I'm not going to go into detail here, but it is basically just a high-pass filter, a passive high-pass filter. And what it does is it removes any DC offset from your input signal. So it will not in all cases, but it will mostly like recenter your wave if it has a DC offset. So if it's pushed up or down here on the graph, basically, because normally what you want with audio signals is you want the center of the wave to be at the 0 volts line. So ground should be the center, and then it should swing up and down from that point. And by using AC coupling, in many cases you can ensure or you can enforce that, basically. Okay, so that's what we're going to do here. That's very simple. And then we have basically two options here. We can either use a non-inverting amp or an inverting amp with an op amp. I'm going to go with a non-inverting amp for now. And what we want to do is we want to decrease the volume of this oscillation. So right now we're at 5 volts peak to peak, and we want to go down to, no, it's 10 volts peak to peak, and we want to go down to 100 millivolts peak to peak. So what we're going to do is we are just going to use a simple plain voltage divider. And I will have to try some values because right now I can't exactly tell you what it was, but I think it was something like this. Okay, so let's run this and see what happens. Okay, I think it's too much. I'm pretty sure it's too much. So we're at, yeah, it's like 150 millivolts peak to peak. So we should probably drop this down a bit. Let's see what we get now. Oh, it's actually too extreme. Interesting. Could just raise this one here up. See what we get now. Oh, of course, even less. How stupid of me. Okay. This is annoying because I don't have other resistivers at hand right now. Maybe if I use a 22K here. No, that's too much. No, you can see it's distorting. You can see how the triangle is getting round. Oh no, it's 11. I wanted to do 22. Yeah, that actually looks okay, I think. That looks okay. Cool. So we have scaled our input signal down successfully with, we first AC coupled it to make sure it's properly centered around 0 volts, and then we've scaled it down, and then we buffered it, and so that's basically this part of the circuit completed. Okay. And then what we have to do is, first of all, what I'm going to do is I'm going to get our CV. Or should I rather say, no, we are going to start with the inverse. So let's just assume that we have the kind of correctly dimensioned control voltage input. So it should be between 0 volts and around 600 millivolts. Because if we go higher, like if we apply a higher voltage to our diodes, then at some point they're going to open up so much that they basically turn into a short circuit. So then it's going to waste a lot of current, and it's just generally not a good idea. So I would say like around 600 millivolts should be the maximum of what we're going to use here. So let's just assume that we get these 600 millivolts. We're going to worry about that later, like how we treat the input signal here to make that voltage. But what I'm going to do then is I'm going to now try to find a way, or I know it works, but I'm going to invert this voltage so that we're able to apply the inverse of this voltage to the bottom. I'm always going to say of our ladder. It's not really a ladder, right? It's just 2 diodes. So yeah, let's invert the voltage. And we can also do this with an op-amp. And the way it works, it's actually very easy. It's getting quite large, actually. Okay. So I'm going to put this here. Okay, so the way it works is we are going to use this op-amp as an inverting buffer. And if you see my filter video, you already know how this works. It's very easy. What you do is you ground the non-inverting input, and then you set the op-amp up like this. And the important part is that these 2 resistances need to be equal. And it doesn't matter like what's the best word for that? What the dimension is. Like it can be a 1K and a 1K. It can be a 100 ohms. But the smaller you go with the resistors, the more current you're going to waste, because this op-amp is going to like continuously push out or pull in current here. And if the resistors are very very weak, then it's going to use up a lot of current. So that's why it's advisable to go like medium big. And I mean, it's kind of arbitrary that I'm using 33Ks here. I could also be using 47Ks, 68Ks, like 100Ks, whatever. I just read somewhere that just as a general like rule of thumb is, don't go like super small. So don't go down to the 1, 2, 3, 4, 5K range. Don't go super big, like don't go above 100K. It's supposedly it's better to be somewhere in this range. So 33K, 47K, something like that. That's what I've read. But yeah, I mean, it works either way. So then we connect, no, actually we don't do that. So first of all, we connect our input CV to this gentleman here. And then we can already try and see if this works. So we are currently, like this is set to 600 millivolts, and we are feeding this into our inverting buffer. And what we get here at the output is roughly about minus 600 millivolts. So it's the inverse. Sorry. So it's the inverse, so it's exactly what we are looking for. And we could now just connect this straight up to the diodes, and I think it is going to work. Let me try it out. So yes, you can see there is a shitload of current flowing through our diodes, but it's actually not that much. Like at bottom right, you can see I equals 830 microamps. So even though this looks quite dramatic, it's actually not that bad. So if we turn on the current speed a bit, then maybe this is a more realistic kind of depiction of what's happening. But yeah, okay. So right now we're at 600 millivolts. So our output is actually swinging in the microvolts range. And if we turn down the voltage here, then you can see that the volume of our oscillation is continuously increasing. And the nice thing is that since these are diodes, the relation here is actually exponential. So for a linear increase, this is important, like we're going to have to deal with this as well. But as you can see, like for a linear increase in voltage, you actually have a logarithmic decrease in volume. I think that's the right terminology. I'm not a mathematician at all, so sorry. And the other way around. So, you increase it, and at first it only gets louder slowly, and then it just really picks up the pace, and then it just really escalates. And that's actually, like, for me, that's what I want. I mean, I know that I think there are also VCAs that act linearly. So for a linear increase in control voltage, you get a linear increase in amplitude. But I think like the more natural sounding, in quotation marks, VCA would be an exponential one, so that it reacts to a linear increase in control voltage exponentially, because that's how our ears work. So like that's why the decibel scale is so weird, because it's kind of tailored to our ears, and we perceive volume like kind of on an logarithmic exponential, I don't know, curve. That's all I'm going to say on that topic, lest I talk myself into a hole. Okay, so I will check the comments again and see if someone has a question. Isn't 100k input impedance a standard in your rig? Kind of, yeah. You see it a lot, definitely. Any other question? Hey, I recognize that VCA design from a PSK modern circuit. Oops. Actually, I'm not lying. I didn't look this up, so the resemblance there is then coincidental, I guess. Okay, but there are no other questions, so let's get back to it. Okay, so one thing that I said, like I was just reluctant to directly connect the op-amp's output to the bottom of the ladder here. And the reason for that is that I'm worried about my op-amp. Because the problem is that op-amps are not almighty. Like, they can't push out or pull in an arbitrary amount of current. Like, they have their limits. And that limit is actually, it's not that high. So what I've learned generally is that you should put a 2K resistor before the output or after the output of your op-amps, just to protect them. And the problem is if we just did it like this, like my first, like when I read this, my first idea was, okay, well then I am just going to put in a 2K resistor right here. And I thought this is going to handle stuff. But as you can see, that is actually a fallacy. Like right now you can't see it, but okay, let me bump this up. So right now the voltage here is at 600 millivolts. So the voltage here at the top is also at 600 millivolts naturally. But if we look here, we can see that we are only at minus 393 millivolts. And this is kind of what happens if you just put a resistance kind of in series here like this. And I can't, or I don't want to like go into it in detail, like why that happens. But this is basically why you can't put a resistance just right here if you want to have the desired voltage at this point. Because if you look here, you can see, oh, working perfectly, you get a minus 600 millivolts, but this doesn't translate to the point after the resistor, so this doesn't work. So what we need to do is we need to, oops, I could have just left it here. We need to put our resistor here, and we don't connect our other resistor here, but rather what we do is we connect our resistor right here. And now what happens is we get our minus 600 millivolts at this point, and we do that basically by forcing our op-amp to work harder than it normally would. So now the output sits at minus 2.3 volts, and in effect, after this resistor, this gives us our minus 600 millivolts. So we are kind of tricking the op-amp into working harder, and we're kind of enforcing the correct voltage at this point. And that's how we do that. And you might have also seen this in my diode ladder design, diode ladder filter design. Same concept. And yeah, all this does is just protecting the the input of the op-amp. Because in the worst case scenario, like if we really like bump up the voltage here, like let's say the maximum voltage here is 5 volts, then you can see that there is a shit ton of current flowing. But since we have our resistor here, we're kind of limiting this to now it's 9 milliamps. And now if I delete this and I put a straight connection in here, then we are at 6 amps. Like there's 6 amps just like raw straight up just flowing through the circuit, and this would probably light things on fire and send out smoke and everything. So yeah, don't do it like this. This is very dangerous. So we go back to this, and then I mean 9 milliamps is still a lot of current, but it's not enough to damage our op-amp. So this guy is safe right now. So that's why it's advisable in a situation like this to set it up like this. Simple. Okay. So I will drop this down again to, let's say, 650 millivolts. And now we're actually already almost there. Now all we need to figure out is how do we get our input voltage, because the problem with this, of course, there's 2 problems. First of all, right now the input voltage could be 650 millivolts at maximum. So as soon as we get a bigger input voltage than that, I mean, you can do that, you can send it in, but it's going to be impractical because everything above this is going to get just a completely quiet output. So there's just going to be no output. And so the range would be really squished. So the usable range of this VCA is basically between 0 volts input voltage and 650 millivolts, or maybe a bit lower than that. But that's kind of the range in which it kind of works. And at 0 volts, it would be really loud, and at 600 to 650 millivolts, it would be really quiet, or just, there would be no signal at all. And so what we need to do naturally is we need to scale the incoming CV down to be within that window. So we want it to be within the window of between 0 volts and 650 millivolts, give or take. Okay, and this by itself is, again, really not, whoops, sorry, you saw my cheat sheet. This by itself is really not hard. Because all we need to do is we need to get out another op amp like this, and we put it right here. Whoops, no, like that. And for now, I will just use a regular buffer, and I will put in a variable voltage here. And what we should kind of calculate with is what I like to do is I always like to prepare like for the worst case scenario. So the worst case scenario in my case, since my synthesizers are using 12 volts minus 12 volts supply voltage, the worst case scenario is that someone blasts in 12 volts into the input. So I'm going to start out with a with a 12 volts CV input, and we're going to make sure that pushing in 12 volts CV should be kind of scaled down to around 650 millivolts. Okay, or maybe a bit more. We will see that later, but for now, this is kind of the reference that I'm working with. Okay, so what we do, very easy again, we just use another voltage divider. So we put one in here. We can go with 100K, we can go with something else, but as someone has mentioned earlier, 100K is kind of the standard in Eurorack. Okay, so with a 100K and a 1K, we get just 118 millivolts, which is not enough actually. So we actually need to increase this by a bit. And this is still not enough. So let's go up to 4K7. And now we're getting somewhere. Now we're at 538 millivolts. Yeah, good. Could be even a bit more. I think I have some 680 Ks lying around. And this is already a bit too much. So we should drop it down. I think I have some 5K2s also. Yeah, this looks more like it. Maybe we just go with this for now. We can always change it. Okay, let me rename this label. This will be our CV. And just in theory, we should now have something that works. But what you will probably see is two things. First of all, the range is really small. So if I just go like very slow here, you can see that at, I don't know, something like 4 to 5 volts, the signal already disappears. So this might be a problem later. But the other issue that is much worse is that the relationship between CV and amplitude is just the wrong way around. It's just backwards. Because right now, if the input CV is 0 volts, then you get the full volume. And if you have like something like, I don't know, 6 volts, then you get, then it's quiet. And this should be, normally, traditionally, this would be the other way around. So you would have 0 volts input should be quiet, and if you increase the voltage, it should go louder. Okay, what can we do? Very simple. Instead of a non-inverting buffer here, we use an inverting buffer. Okay, so let me pull this stuff here away. And what we will do is we will simply ground this point, and then we will do just the same thing that we did here. One good thing that this brings with it is that we don't need to use a voltage divider here, but instead what we're going to do, with the buffer here, we used identical values for this and this resistor because we wanted to have a gain of -1. So you get 600 millivolts in, you want to have minus 600 millivolts out. So this is a gain of -1 is what you say. But what we want here is we want a smaller gain. We don't want a -1, so we don't want to have minus 12 volts for 12 volts input voltage. But instead we want to have, like I said, like something like minus 650 millivolts for a 12 volt input voltage. So we need to configure our inverting op-amp here in a way that it scales the input signal down, basically. So again, I will just put in random values and then we will see what works. So let's go with this. And I will try to do something like, wait, where are we now? Okay, so as you can see, it's actually not that easy because, I mean, the problem is that still we have 0 volts input voltage, and our signal is completely loud because, of course, if you take 0 volts and you feed it into even an inverting op-amp, it doesn't matter, 0 times anything, 0 times 1, 0 times 10, 0 times minus 500 something is always going to be 0. So 0 volts input will get you a 0 volts output. So this is not what we want. So this doesn't work. So I mean, the general direction is right. So you can see as I increase the voltage here, so let's go up to, I don't know, 5 volts. Then we get a negative voltage here. And interestingly, this also makes our output signal louder, as you can see. So I increase this, and it's not much, but it gets a bit louder. If I decrease it again, you can see that it gets a bit quieter. So in general, it's working. So if I push this slider to the right, it's getting louder. If I push this to the left, it's getting quieter. So the direction is right now. The problem is just kind of the center or the alignment. And this might seem like a kind of insurmountable problem, but it's actually very easy. So what we need to do is we need to kind of recalibrate. We need to kind of recalibrate this op-amp. So right now, what it's doing is it is looking, like in very simplified terms, it is looking at the voltage that we feed it, and it's kind of comparing this to the voltage that it has here. And then it's kind of, just inverting it in relation to the voltage here. So if I put in about 1 volt here, then it will take this voltage, look at that voltage, and it will kind of say, okay, so this voltage here, which is 0 volts, is going to be the axis across which I'm going to kind of mirror or invert the voltage here. And right now, I mean, just to make this more clear, if I make this just into a gain of -1 op-amp, so right now it will take the 1.2 volts, it will look at the voltage here, which is 0 volts, and so it's going to say, okay, if I jump from 1.2 volts across the 0 volts line, just the same distance again, where do I land? Well, I land at -1.2 volts. Naturally, because if 0 volts is just the center axis across which I'm jumping, then -1.2 volts is going to be on the other side, basically. But what happens if instead of 0 volts we just apply a different voltage here? So what we can do is we can just, for now I'm just going to pick this. So I'm just going to pick a different voltage. So right now I have 5 volts, sorry. So what the op-amp is doing now is, again, it's looking at the 1.2 volts. It's looking at the voltage here. Now, the funny thing is that now the voltage here is actually higher than the voltage that is getting here. And if you, wait, maybe I should show you, like, for one video I did this illustration that might help actually right now. I'm going to show you. Okay, let me switch to the sheets here. Okay, here's my stack of stuff that I've drawn. It's actually a lot now. I think I saw the sheet that I meant like 2 days ago. Ah, there it is. Perfect. Okay. So maybe this makes a bit more sense. We will see. Okay, so what I've drawn here is, I mean, here on the y-axis you have voltage. Here you have the ground or 0 volts line. And then what you can see is if the op-amp is configured to have a gain of -1. So if these two resistances are equal and you apply 0 volts to the non-inverting input, then this is what happens. It looks at the input voltage and will just jump over the mid-axis. It's going to come out on the other end. And so because the distance between the voltage here and ground is this big, then it's going to, jump the same distance and land down here. And now what happens if we change the voltage that we send in here? So if we, in this case, if we increase it to 500 millivolts, so if we send 500 millivolts into the non-inverting input here, and we have the same input applied to this terminal here, then what will happen is instead of having our mid-axis down here at the 0 volts line, we're going to have our mid-axis at the 500 millivolts line. And if we jump the 500 millivolts line from here, from our input, then we're going to actually come out at 1 volt. Or a bit less than that. It sounds a bit confusing, but this is basically how it works. I hope this makes sense. So let's change back to our simulator. Okay, so right now in this case, we would jump the 5 volts line from 1.2 volts input, and we come out at 8.8 volts. I mean, the exact values in the math is not that important at the moment, but just as a concept, just remember that if you change the voltage at this terminal, you can kind of move around the axis against which the op-amp is inverting the input voltage. Okay, so what we can do now is, if we drop this down, like we drop it down to, let's try 300 millivolts. So what do we get then? Well, now we get for 0 volts, now we get 600 millivolts, which is exactly what we're looking for, right? Oh no, is it? Yeah, it is. Right, because 600 millivolts here means that we get minus 600 millivolts down here, which means that the diodes are so active that our signal is very quiet, basically. Okay, now the problem is, since this is still configured to have a gain of -1, if we now increase the voltage, it's going to go up like extremely quickly. So now we're already at -1 volt, and if I increase it even more, now we're at -5, like this is way too much. So what we have to do is we have to drop down the value of this resistance here. And then what happens is at 0 volts, it's still the same thing. We get an output voltage of, oh, interesting. It's not the same thing. Of course, if the gain is different, then the way that we're jumping this mid-axis is just going to change. Okay, so let us try to adjust the value of this resistance here. This is not helping. If I make it bigger, I know it is helping. 390. Okay, so I guess I also need to increase the voltage here. That was wrong. Let's go up to 500 millivolts. Yeah, that looks good. Okay, so 33K, 10K, and 500 millivolts here gives us 650 millivolts for 0 volts. Okay, and now if I increase the voltage here, you can see that it is rising beautifully, but maybe it is actually a bit too quick, because now I'm at 5 millivolts and we're already at maximum amplitude. So maybe we should, stretch it out a bit so that the maximum amplitude is kind of achieved a bit later. So 5 volts is a bit too low for my tastes. So what I will do is I will reduce the gain of this. Op-amp. So let's go down to 4K7 for now. But then also what we have to do is we have to adjust the voltage at this point, so that we again get our, 680 seems okay to me. You will notice one thing. I haven't really figured out how to prevent this, or if it needs to be prevented at all. But you can see that when the diodes are very on, so when the output signal is very low, we have an offset here. it's just 5 millivolts. So, you know, it's just 5 millivolts away from the 0 volts line. But it's not ideal. It's there. I'm going to have to live with it for now. Okay, so let's try it again. We'll try to raise the CV. And we can see that it's slowly getting bigger and bigger and bigger. And now we're at 6 volts is the maximum. That might still be a bit too low for my tastes, I would say. So let's try to maybe drop this down. What do I have? I think I have a 2K7. And then we have to adjust this point again. Oh no, this is actually okay. I would say 650 millivolts, something like that. Okay, let's retry. Now we'll increase the CV. Okay, and we can see it's rising and rising and rising and rising and rising. And we get to the full volume at something around 9 volts, which coincidentally I think is what my envelope puts out. So I think this should be a nice fit, actually. We might want to increase this a bit later, but for now, let's just worry about how we get this voltage. But first, I will check the comments again to see if there's anything unclear. Okay. Would putting a voltage on the positive input of the CV op-amp help? Not sure what you mean. Maybe this question was before I presented the solution already. The nonlinear part means if your input signal is... Sorry, I'm really bad with formulas in math, so I can't help you there. Kyler, how much energy an oscillation loses per radian of the cycle? No idea. If you connect the lugs of the potentiometer inverted. Also not sure what you mean. Would caps on the CV output help to filter out noise from the control lines? Probably, but this is something that you would, I think, do if you kind of refine and finalize the circuit in the end. It's maybe a stupid question, but couldn't you get rid of the offset by using AC coupling again? You mean after the amp? I think those questions I've already answered. That was me answering someone's question. Okay, maybe I should just just go through with what I have in mind, and then in the end we can do a Q&A. Maybe that gives it a bit better structure. Okay, so I will go back to the simulation. Okay, so for now, for me I've established that this should work okay. I mean, yes, we have the offset here, and yes, one thing that you will notice is that the oscillation is not completely gone. So if I go to max scale, this looks very alarming. It looks like there's a lot going on here, but it's actually in the microvolts range, and we can actually I see something. I'm not following my own advice. As you can see here, I forgot to add in the output protection. So right now this op amp is just like happily running wild. Which but maybe it's actually not necessary to have it at the top, because I mean we already have this 2K resistor here, so maybe we actually don't really need it, because like even if I really were to push this guy up, so let's say we put in 2 volts here, I don't think that this line can actually go beyond 13 millivolts. Milliamps. 13 milliamps at 12 volts. I guess for now it's still okay. But I mean, no. Let's be kind of thorough. Let's keep our conscience clean. So I will also add in our output protection here. So just exactly the same concept. What we do is we put in a 2K resistor here. Boom. And we connect it here. And now we get our now we get our 650 millivolts here without endangering our op amp. Okay, so one thing that I might want to do is I might want to increase the voltage at this point, simply because this is already at 7 milliamps. That's a lot of amps actually. Okay, but now the oscillation is like even quieter. Like this is the kind of trade-off with this design. Like the problem is you are never going to have no oscillation here. Like it's never going to be completely squashed. You can only like get it like really, really silent. It's never going to go completely away. And the question is, you know, like the price that you pay for a more quiet signal is more of a current that's flowing through here. Now 7 milliamps, I think it's still defendable. I think 7 milliamps, it's kind of wasteful for the VCA being off. But I mean, like an LED is pulling what, like 10 milliamps, something like that. So I think this is still acceptable, probably. Correct me if I'm wrong, or if you see this differently. And also, I mean, of course, with a different kind of design, you wouldn't have this kind of wasted current constantly, but that would probably make it more complex, or at least, you know, involve like a completely different design. So just so you know, for now, this is the kind of trade-off that I'm asking you to make here. And we could kind of fine-tune this, like maybe if I go down to something like 650 milliamps at this point, then we get what? Then we get 6 milliamps. You know, but for that now the signal is again like a tiny bit louder. So you know, you're going to have to decide with how much noise you can live, and then on the other side, like with how much wasted current you can kind of live. Oh yeah, again, one more thing that you could do to make the signal here more quiet, you could increase the value of this resistor even more, but I think this would make the circuit even noisier, so I think I would advise against it. Okay, so the final boss. What we want to do now is we want to, of course, make this doable, because we can't magically, you know, just get 650 millivolts exactly from somewhere. So what we are going to need to do is we are going to need to get this from the power rails. And the way that we do this is actually very simple. We're going to use a trim pot. So, boom, put a potentiometer in here. And then what I will do is I will connect one side of it to plus 12 volts. I will connect the other side straight to ground, and I will increase the value of this pot, because, you know, it's very wasteful. If we used a 1K trimmer, it would be very, very wasteful. So I only have 20K trimmers, so that's what we have to deal with. I mean, if you had 100Ks, it would be even better, because I think we don't need to worry about noise here. So a larger trim pot would mean less current wasted. But this is what I have, so this is what we're going to use right now. We should give this a proper name. This is the CV trimmer. Sorry, I'm not very creative today. Okay, and then what we want to do is we want to set this trimmer so that, oh, interesting. No, this doesn't work. Okay, because, yeah. Okay, so we need to get this down to 600 millivolts. So we need to move this in this direction, and now it's going down. Right now we're at 4 volts, and now we're at 1 volt, and now we're at 772 and 535. Okay, no, yeah, that looks good. Okay, so now we should be able to increase the, yes. Okay. And this is how I would do it. And luckily for you, I'm not going to bore you with looking at me building this on a breadboard. Instead, or before this, I already like set most of it up. So what we're going to do now is we are going to check this out on the breadboard. I haven't properly tested it, so we will see if this, works. But as you can see, I've kind of achieved my goal. So my goal going in was I wanted to use no more than 4 op-amps, because then you can realize this with just one TL074 IC. You don't need to use multiple. You don't need to use another TL072. For me, this is nice because, you can get a kind of compact layout. Also, I mean, this might look quite complex, but if you know what everything does, then this is actually like really simple, because I mean, this is just an amplifier. This is just an inverting buffer. This is a bit more complex, but also not that complex. And I mean, this is also trivial. So I think this is like a quite nice, like simple little thing. And now we will try and see how it sounds, how much it distorts. Maybe we can also try play around with the input volume to see how it sounds if we get a bit of distortion out of it. But yeah, let me quickly set up the breadboard, and I will check the comments again just in case you guys have any questions now. Too bad I like breadboarding. No, we are breadboarding. I just wanted to spare you just me setting it up from scratch. Where can we sign the petition to name this 2-diode configuration River? Glad you like it. Yeah, if your design is based on forward biasing the diodes, you're just gonna have to live with the current they pull. True, yes. But like I said, I think like 7 milliamps is going to be okay. So I'm going to switch over to the breadboard, and I hope you guys can see. So like I said, this is basically all set up. So what I've done is I have used this op-amp over here to condition our input signal. So this right now is my kind of CV source. It's just a potentiometer that is connected to ground and then the positive rail. So with this pot, I can send in any voltage between 0 and 12 volts. And then, like you saw in the schematic, I'm sending this into this op-amp to be conditioned. Right now, which is what I've done earlier, right now I've set this up with a fixed value voltage divider to scale down the input. I'm going to now exchange this with a trim pot. So Peter, you're going to see some breadboarding and maybe some stupidity. But yeah, this is what we're going to change here. The rest, I think, should be good. So right here, I have my my inverting buffer that is going to the bottom of the river, of the diode river, if you want to call it that. And these are just the resistors that are going to the diodes. And then what we have here is like this is basically the center point of the diodes. Like this is the kind of junction through which our signal passes. And then on the other side, we have our input coming in here. I am AC coupling it through this capacitor and this resistor. From here, we are then going into this op-amp, which is basically the buffer, and we are basically just scaling it down here. And then what you can see here, like this is basically the final op-amp. This is the final, this is the amp that will blow up the signal, basically. And you can see that this point here, which is the non-inverting input of our buffer, is connected to the junction, to the river. And it is also connected to, wait, what is this? I have to remember. Of course, it's connected to the input signal, right? It's connected to the input signal through our 1 mega ohm resistor, and it's also connected to our junction into the river. So this is basically the path through which our signal is going to disappear whenever the diodes are very active. And that's the way it works. So, this is kind of like a leak, and this leak gets bigger as you increase the control voltage. That's how that works. Okay, but now the only thing that we have to set up and change is, like I said, the voltage that I'm feeding the non-inverting input here. So it's the kind of mid-axis voltage. So what I'm going to do is I'm going to remove this resistor here because we don't need it anymore. And I will also remove this one because this is the other guy that is making our voltage divider. And now I will need a 20K trimmer. Give me a second. Luckily I have one because I used it earlier here. Okay, I will set this up over here. Whoops. And then in there. Okay, and I will not send this into our circuit for now, because what I want to do first is I want to set it up and get the right voltage there. So I will set up my power supply, and then we will use my multimeter to kind of fine-tune this trimmer. This is a full cap. This is for AC coupling, exactly. It's like I explained earlier. Like, we want to make sure that the incoming audio signal is properly centered around 0 volts. That's the idea there. You can't really use an electrolytic because you are passing audio signals through it. You're passing AC signals through it, and the polarization is going to be a problem because electrolytics don't like it if the voltage at their negative terminal is above the voltage at their positive terminal. And the worst case, this can cause it to explode. So it's something you should avoid, and that's why you shouldn't use electrolytic. You can use ceramic or tantalum, I think, work too. Or no, those are also polarized. Like, any capacitor that is not polarized will work for the AC coupling. Isn't the AC coupling going to harm non-symmetrical wave inputs? It's not going to harm them. It's going to, shift their center, which is something that I've fought with in the past. I still see, like, most circuits are going to have AC coupling at the input, because it's going to catch many DC offsets, not all. Like you said, if you have a pulse wave, for example, like just a 5% pulse wave, it's going to mess with it because it's going to push it upwards, which might cause trouble. But probably have to try it, see like how bad it influences the operation of the circuit. But this is a problem that you always have. You always have this problem with any kind of processing, basically. So this VCA isn't meant for CV. No, it is. For now, I'm just using the potentiometer here just for demonstrating. Okay, but now let's set up our trimmer. Okay, as expected, we have 0 volts right now, which is good because my power supply is off. You can use a polarized cap for AC coupling if you account for offsetting that. Yes, definitely, but I think it's more trouble than it's worth now. Like, you can always buy a non-polarized cap for a few cents. So, I mean, sure, if a polarized cap is all you have, then maybe you're desperate, you can do that, but I would advise against it. It's adding complexity where you don't need it. Okay, let's turn on the power supply. And we should see something. Yes, we have 10 volts right now. If you can see this. Now I can see it better, I think. Okay, so let's try to get this as close to... I think I would like to get something like 700 millivolts. Something like that. Whoops. Or was it 600? We'll see. Ah, this is a nightmare. Okay. Ah, you mean CV for the VCA, as in you want to control CV with the VCA. Yeah, sure. If you want to do that, then you shouldn't use AC coupling at the input, definitely. Then you should leave that out. Electrolytics are common in audio amps and they can cause the thump when you turn them on. If you hear a little delay click instead of a thump, then relays you... okay. Come on, please go down. And this looks good. Okay, I will have to look up what the value was exactly. Give me a second. $650 millivolts is what I wanted to get. Okay. Okay. Yeah, I mean, close enough. Okay, so this works. So oops. So then I'm going to connect the trim pot to the non-inverting input of this op amp, just to set the mid-axis basically. I think I'm going to do this quick and dirty, so don't hate me, please. Because in the end, we just want to know if this works, right? Okay. This looks okay. Moment of truth. A smaller trimmer, what do you mean? For, I would say a resistor or divider to feed the positive side of the trimmer would make it easier to trim. Yeah, definitely. Like I said earlier, like once you put this into a proper module or something like a refined circuit, definitely you should use a different kind of trimmer. But I mean, for now, I'm just winging it. Okay. Whoops, sorry. Let me turn this down. And now we'll see if this actually works. Okay, nothing. Good. Okay, it seems to work. Okay, so the next thing that I would do is I would try to send in some sort of CV. So I will go with an LFO first. And I will just send it in where the potentiometer was before. So just plug it in here. Whoops. Okay. Let me turn the LFO down, and then we will see what happens. So of course right now nothing happens. And now we'll turn up the LFO. Yeah, that sounds good. Oh no, that doesn't sound good. Do you hear that noise? It's like a very distinct, strange noise. You know, just when it's closing, I think. Okay, so I have a theory about that. Wait a second, let's try my envelope. Because, I mean, the difference is my envelope is not going below 0. So my LFO is going, I think it's swinging from like -9 to +9 volts at the most extreme. And my envelope is kind of pushing out something that's between 0 and 9 volts. Okay. Seems like I was right. Okay, so what I think the problem is, yes, Matthias already said it. If the LFO is bipolar, wouldn't it be a problem? Yes. I think the problem is that whenever the LFO goes negative, then we kind of reverse bias the diodes. So we kind of push them in the other direction. And I think, like I also explained this. Sorry, I'm going to remove this. I also explained this in my latest video on the filter. I think that whenever the diodes like have to quickly switch from being forward biased to reverse biased and vice versa, I think then we get this. This ugly noise. So probably what we need to do is we need to make sure that there's no negative voltages coming into our circuit. And so what we can do just very quickly is just put a diode at the input. This will just to say it right away, this will introduce some nonlinearities in the beginning. So in the lower spectrum of the sound. Let's try it. Diodes are too fast for that effect to show up in audio applications. You sure? I'll try it, we'll see. Because, I mean, in the filter design, I also had the problem, and I put a diode after the CV processing, basically, and this fixed the noisy issues. I will just try it. We'll just put it in. Let's see what happens. Question is, where do I put it? Maybe for now we'll just put it like right at the input. If it doesn't work, we can try other things. Sorry. Okay. Boom. Put this in here. And then see what happens. Okay, right now I still have the envelope plugged in, so. That sounds okay still. Yep. Sounds good to me. Okay, then let's try the LFO again. I will turn it down for now. And okay, it's super fast. Okay, so the noise is gone actually. I'm very sure this is actually the problem. So we want to prevent these diodes from becoming forward biased or reverse biased rather. So this is a crude solution, but for now this this works. So let me try to put in a sequence and hear how that sounds. Give me a sec. Sorry. Yeah, I should have planned this beforehand. Okay, sorry for the delay. Okay, that sounds okay to me. Yeah, that sounds good to me, actually. Okay, questions. There are some questions. Give me a second. It sounds nonlinear because of the clipping effect of the diodes. Yeah, I think that like what I meant is, of course, it takes a bit for this diode to open up. So if you are like in the 100, 200, 300 millivolt range at the input signal, then the signal, you know, the diode is not going to open up completely. Also, you have the forward voltage drop, which are all things that are going to kind of mess with the response to the CV. So it's not going to be perfectly kind of linear. But I think for now it's still an okay workaround. I would look with a scope. I never trust my ears that much. You mean for distortion? We can definitely do that in a second. I wasn't paying attention. How did reverse biasing the diode change the sound? It's just on the transition. You know, it's on the transition from the CV being negative to the CV going positive. You have this. I don't know how to describe it. It sounds a bit like you're plugging. Not like you're plugging something in, but there's like this this kind of noise, like this clicking noise there. That's very ugly. What to use for signal input? It's just directly coming from my VCO, and now I just sent in a sequence from my sequencer, and that's all. And then I also trigger the envelope from the gate out from my sequencer. That's what that was. And I think that both the square and the saw sounded very, very saw-y and square-y for my ears. But we're going to mess with the volume of the input signal to see like what happens. You know, if we push the VCA, like how it's going to distort the sound. How did you program this sequence? Like I said, with I have a BeatStep Pro. It was just in memory. You can offset the LFO input to be always in the positive voltage range by using capacitor followed by a voltage divider. Yeah, you can. You can also use an op-amp clipper, which I discovered today. I'm of course going to clip the lower half of the CV, but it's also very effective, and it doesn't have like all the problems that I just described here with the forward voltage drop and the non-linearities and everything. So it might be something that I'm looking in for when I polish this up, basically. Input has a lot of glide in it. Yes, the sequencer has a lot of glide steps there. James Sherman, hello. Moritz Klein, hello. Hope you're doing well. Please play the same sequence without this circuit just to compare. Sure, we can do that. So now I will just send the sequence directly to my interface. That's how it sounds without a VCA. And now we will hear what it sounds with the VCA. So to my ears, it doesn't sound very distorted. But like I said, we can check later with your oscilloscope, and we can also try to increase the input volume to see what it would sound like if it did distort. Could you try to quickly breadboard out this even simpler VCA and compare performance? Maybe in the end, if we still have time. Like for now, I would like to focus on this. I didn't realize you were talking about the diode for the CV input. I was thinking about the two signal clippers you were showing in the beginning. No, just simple diode at the beginning. It's very easy. Hi Christian. A bit late. What circuit are we playing with? No, actually, I made a point of not using an OTA. Instead, I just use diodes because right now I'm on a diode trip. So I wanted to see how far I can get just with diodes and op-amps. So this is the VCA that I cobbled together just from one single TL074 and two diodes, basically. That's all. Oh yeah, you all answered the question already. He wants to avoid using an OTA for fun. Exactly. I think fun is in restrictions. Like whenever you restrict yourself, you can get creative and have fun. If you need a diode on the input, either bias it as to not suffer the offset or use a voltage for. Yeah, like I said, definitely. When I polish this up, I will make sure that I don't just simply use a diode here. But for now, I think it's good enough. Did you already choose the lucky recipients? No, I'm going to it's very stupid. Like I should have used some kind of site or software to kind of map or keep track of who is in the raffle. Instead I just have a document with all the names, and in the end I'm just going to drop them into a random generator and just pick two people at random. And I said that I'm going to do this next Friday. Then I'm going to pick the winners, and I also will do like a short announcement video. Was this a ramp LFO? No, it was a triangle LFO. Can you describe the problem you're hearing again, please? You mean with the... I can show it to you again. I can send in our LFO. Okay, so right now I'm feeding it the triangle LFO. Or not. Weird. We have no input. Okay. Now we have an input. Okay, right now I have the diode in, so there's no problem. No, there's nothing here. But if I connect this directly, I think you can hear it on the lower end. No, focus on whenever the signal is gone. If I make it faster, I think you can hear it. Almost sounds like a second oscillation, like a very slow oscillation whenever the signal is gone. And like I said, I think that this is from, when the diodes go from forward biased to reverse biased, or the other way around. That's, I think, basically the problem. That's why the diode solves it for now. So we would need to review your random number algo, since true randomness is a tough thing with a computer. Yeah, that's true. I mean, I could also roll the dice, but it's already like 500 names, so I would have to either roll a lot of dice or have a very big dice. Or I could throw like darts at a wall, something like that. You might be hearing the output offset switching polarity. Remove the bottom 2K protection resistor and listen if it's gone. We can try that, of course. The bottom 2K. So you mean this, I think, is the one that you mean. Let's try it. Okay. And another one of these. Okay, let's give it a try. Might actually be gone. Yeah, I don't hear it anymore. Perfect. Nice solution. Very good, thank you. That was a good tip. Okay, what else? I can't hear the difference. Yeah, maybe it's like through YouTube with compression and everything, but it was definitely there. It was unnerving, I can assure you. Would be easier to hear with a pure tone signal being amplified. Yeah, I don't have a sine wave oscillator, I'm sorry. That's why I can't use it. Low frequency thumping, yes, exactly, that's what it was. I can just hear it when you went faster. Yeah, it appeared to be frequency dependent. I already underpay Moritz to be the winner. I can confirm that. Roll a number ball. Would have to be a big ball, no? Wasn't the bottom 2K the current limiter? Yes, it was, but I also have one at the top. So I have one at the top, I have one at the bottom. And since the two op amps are only connected, to each other, then if we have a 2K on the top op amp, it's still enough, because the 2K limits the maximum amount of current already. And I mean, we're making sure, like through our scaling, we're already making sure that the diodes never get like overly forward biased. So this should be perfectly fine, I think. So again, good tip with removing the bottom 2K, even though I still don't really understand why it fixes it, but yes. Will you be sharing schematics? Definitely. I have already drawn it up. I will post it in the description of this video, as usual. I will be doing that. Sample a transistor avalanche for random numbers. Yeah, it might actually be a cool video if I did that. Where we're going, we don't need current limits. Yep. Should be totally safe. Yes, I agree. Okay, so what I want to do now, you can remove the 100K resistor from the high pass because you have a 22K. Yeah, probably, you're right. I can probably remove that. Again, let's try it. It's not that I don't trust you, but I want to be sure. Yep, that still sounds good to me. I just got in when you were testing it without it in Falstad. Yeah, that was when I was testing it without both 2K, so I had no current limiting on there. So that's when I got the 7 amps. Okay, so what I would say, what we're going to try now is we are going to try to increase the input signal to see, what it would sound like if we had distortion on there. Okay, so I have the voltage divider in here, and I think the simplest way to do this right now is just to increase the resistor that's going to ground here. So this is the voltage divider. If I just increase this, then we can just put a potentiometer right here, so to attenuate the input signal, and then we can kind of see what it sounds like if we drive it. So first I have to find out what value this is, because I can't remember what I built here. It's often the case. And I really don't, like, I admire people who can just, you know, look at resistors and, you know, they know the color codes, and they can just look at the colors and then they know, ah, this is a 1K. Just beats me, like, how you can memorize all of those. Okay, so this resistor was a 2K, actually. Interesting. Then the other one was, might have been 100K. Let's see. Whoops. True, it's 100K. Okay. So what I will try to do, I mean, first of all, what I will try to do is I will, I mean, I had 100K 2K, so let's try 100K 10K now, which should be orders of magnitude louder, and it should give us some nice crunchy distortion, hopefully. Let's see. $100K goes in, and then a 10K goes in. So I'm expecting this to sound pretty mean. Let's see. I could try, I mean, it's not a sine wave. I could try to feed it a triangle wave. Maybe then it's more obvious when it's distorted. Okay. Yeah. That's definitely distorted, I would say. Okay, so we know that this is really distorted. Maybe let's go even more extreme. If I pull out this resistor here, I pull this guy out completely, then this is not a voltage divider anymore, but instead it's, you know, it will just take in the input voltage as is. So let's see. Yeah, that's pretty intense. Yeah, it sounds like a lightsaber, actually. True. That's pretty funky. Okay, so I think what I would do in the end, like when I did build this, I think I would do it like I said earlier. I think I would put in an attenuator at the input signal, and then I would kind of mark, you know, the place where it's undistorted, and then you can go past that and have it kind of distort the sound. I think it sounds quite nice. I always think that diode distortion is quite cool, actually. Okay, and I think I saw that there were some questions here. There were some questions here. I'm colorblind, so the resistor code is a pretty annoying system to me. Yeah, I don't get it. And I mean, everything else is labeled. Like trimmers are labeled, potentiometers are labeled, capacitors are labeled. I mean, I get it. Like resistors are small, so you know it's hard, but still it's annoying. How would you go about adding a volume knob so it works like a mixer, but it would switch to CV when something is plugged in? Well, I think like most VCAs or some VCAs have a gain knob, and I mean, yeah, you can probably implement this here if you adjust the gain of this op amp. You could probably also, I can try this right now. I can set up this potentiometer as a voltage divider, and I can send in the voltage from here as well as the incoming CV, and then we can see what that would sound like. Or maybe instead of doing that, I can just switch it out here. I think I used 100K here. Let's check it out. Okay. We'll just quickly check this. And it is, 33K. Good to know. Okay, so to make things a little bit easier, I'm going to break out this point to a point over here, and then we have an easier time of connecting the potentiometer along with the CV input. And I'm going to do it quick and dirty again. Oh, and by the way, does anyone else have this feeling like right now the power supply is still on, so the circuit is still active? I mean, I haven't plugged it in, so you don't hear anything, but I always get this feeling like I'm, like I'm operating like open brain surgery, something like that. And if I mess up, then everything ends. So I should probably just turn the power supply off, right? Okay. So this cable here now connects to the non-inverting input of this op amp, which is, this is the, oh no, it's connected to the inverting input. And this is the op amp that's conditioning the input signal. So here we can now send in our input CV, like be it the potentiometer or be it the external input. And I will just use just equal value resistors. So I will make the potentiometer kind of as influential as the, is that the right word, influential? Like as, prominent in the mix as the external CV for now. So the potentiometer is going to go here. We can move it here, it's better. I'm really struggling to put stuff into the breadboard today, I don't know why. Okay, so now we have, or now I will put the CV input in here. And then I will also put our potentiometer back in here. Okay, and now we'll see what that does. Oh, I should kind of calm down the gain, I guess. If I can find the 470, or what was it? No, was it 2K, I think? Maybe this is a 2K, let's check. And it is a 2K, perfect. Like sometimes, I mean, I can't read the color codes, but sometimes just when I look at a resistor, I get like this gut feeling what it might be, and sometimes it's correct. Okay, so just to reiterate, what I'm doing now is I'm sending in I'm using a potentiometer to kind of send in an offset, and I'm also sending in my LFO, and we want to find out like what that does to the sound basically. Okay, so it's still distorting, interestingly, but yeah, I will turn up the gain. Yeah, and as expected, it's basically just an offset. So if I turn it up all the way, it's basically on most of the time, except for, you know, when the LFO is pulling it down. But what we can clearly hear is that this is actually quite distorted. So I will try to replace the 2K that I put in here with a 1K to see if that fixes things. So put that guy in here. Maybe we should check first what the wave sounds like without the VCA. Oh, I'm just realizing that my interface is actually clipping. Okay, that makes it very hard to actually assess if we have distortion here or not. Okay, so what we need to do is we need to calm the output op-amp down a bit. So I will drop this resistance here down from 100K to, I think we might even just go with a 33K, because I mean we want to get it down to line level, and I think it was at 10 volts peak to peak. So if we get it down to like 3, it would actually be okay. Okay, but for now, let me turn down the LFO, and we'll listen to it now. Okay, so this is what it sounds like right out of the module. This is without the VCA. So from here we can kind of check if the VCA is adding any distortion. Do you hear the radio as well? Interesting. I don't know if you can hear, but I can actually hear the radio through this. Okay, this might be because of long wires, but interesting. Let me pump the resistor here up again a bit, because I think the earlier clipping was just because of the interface clipping. Okay. Again, the interface clipping, let's turn it down. And yeah, I think this sounds... I think there's some distortion in there, so I think the values will have to be fine-tuned. But okay, let me check the comments again, just if anyone asks any questions. Where was I? We talked about this. Had to sort a small bucket of resistors during an internship once. Was a nightmare, but at least I know the values by looking at them. Probably, like no pain, no gain. That's how you learn, probably. I'm too lazy for resistor colors. I just measure them. Same. This VCA looks like a weird distortion circuit with VC clipping diodes. Probably it is. Like if you, like we just saw, if you push the input signal very loud, then you get distortion, definitely. Okay, I missed a lot of comments. Okay, I will just start here. You may imitate sine by filtering square, maybe for testing purposes. Yeah, I think the triangle wave was okay. Let me know if you still want to hear a sine. I think distortion may be the feature. Just set up input buffer as an amp and put a drive port after. Yeah, that's what I'm planning to do. The issue with using a filter to get sine is the amplitude will swing wildly with the frequency unless your filter tracks keys. Yeah, I think he meant just like for a static tone, like for a fixed tone. I think for that it would be okay. With that kind of complexity, yeah. I have to run, but wanted to say this is a really cool stream. I hadn't thought about using Dialector for implementing VCA before. Thanks. Yeah, my pleasure. Like I said, I'm going to post the Falstad simulation in the description of this video, so there you can find it. But also, one more thing, my live streams are only available through my Patreon, so they won't be public on my YouTube channel. So if you want to look them up later, you are going to have to splurge on my Patreon. I'm sorry. Can't you just bypass the potentiometer by using a jack socket with a switch? Not entirely sure if you can. Maybe you can. Maybe you could send in the... No, you can't do that. I have to think about it. If I were to order PCBs from China aiming for fastest turnaround time, where would I source them from? I'm in the EU. I can't, I'm not qualified. I have only ordered one batch, which was from JLC PCB. They arrived very, very quickly. They were held up in customs for a bit. Not sure if, I think that there are some PCB manufacturers in Europe. Probably the shipping time will be faster because you don't have to go through customs. But maybe other people can chime in here and have better information than me. This description says we'll be looking at some of my dead simple VCA designs. This is still design one, isn't it? Are there going to be more or saving for another time? I have one more that is just completely stupidly simple. You guys will have to tell me if you are still up for looking at something else, or if we should do it another time, but because this took longer than I anticipated, actually. The last live stream is not on the YouTube channel. Will this be? No, like I said, it's only available on my Patreon as a replay, basically. Do you have a website? Not for now. I only have my Patreon, and there we have a Discord server, and we also have a community GitLab repository. Those are the things that we have. I don't have a website right now. I will down the road, like when I open my web shop, but for now, no. A lot of hobby. Nah, it's all about resistors. You're fighting about resistors. Why synth builders are not interested in making PCBs at home? I see people are building their synth on strip boards or manufactured PCBs, but not DIY. I think it's mostly just convenience. I mean, in the beginning, I really liked to use strip board because I was like die-hard, DIY, wanted to do everything myself. But at some point, I kind of realized, the novelty effect is gone, and I don't care so much anymore if stuff that I'm using has been pre-made. So that's why I kind of switched to manufactured PCBs. I think if you put the video in your view later, you will be able to access it. Yeah, you can cheat around it, definitely, but I would ask you not to do that. What else do we have? Long wires plus diodes with amplification. Yeah, you can pick up some radio signals. Yes, as you saw. But I think this has also to do with this being on breadboard. Like I said, I think if you build this as a PCB or strip board and you don't, you trim your copper tracks a bit, I don't think you're going to have a problem like that. What is the name of your bug running on the table? It's very annoying. I have these, I don't know what the English word is, these are like these bugs that live in the soil of your plants, and they multiply like by the thousands. It's horrible. I have like these yellow stickers that they are very stupid. Like they really like the color yellow. That's why they land on these yellow stickers, and then they are trapped and they die. But I still, many of them die, but there's still many around, so I can't get rid of them. So I just ignore them for now. I know quite a few people who etch their own PCBs, But JLC is so easy and cheap nowadays. Yeah, that's exactly my reasoning. It's so easy of the design of the computer. You just send it away and you get it in the mail. It's just a convenience type thing, I think. As mentioned, could you try to quickly breadboard out this even simpler VCA and compare performance? I will check it out in a second. I'm having a good time up for more. Cool. You asked the chat if you should go on. Schematic will only be available in Patreon. Yeah, it will be in the description, and the video will be available through Patreon. So, I mean, eventually, I'm planning on doing like full episodes on all of these topics. So, of course, I'm going to do a VCA. Of course, I'm going to do a drum module. But you know, just making those videos takes a lot of time because I need to, you know, write the scripts, draw all the draw all the sheets and everything. So there's only so much I can do. I try to have like a 3-week kind of turnaround, like, you know, do a new video every 3 weeks, but this is already kind of pushing it because I have a full-time job. So eventually you will get this content for free. You will also get like a polished version of this for free, but it will take some time. That's the way I want to handle it right now. Oh, hi Brian. Hi Brian. If you keep coming back for more and more boards, then they know they can just develop that into a product and sell it themselves. Oh, okay. I've heard that if you actually bother to protect your IP in China, you can go after them. Not that hobbyists would do it, of course. Yeah. Yeah, that's true. Okay, so first I will take a look at the VCA that Mr. Slehofer posted. And we will see what that is all about and if this is something that we can just whip up quickly. Okay. Put this in here. Okay, I will show you what I'm seeing. But right now I'm not really sure what I'm seeing there. I guess this is DCV and this output level control voltage. You're using a PNP transistor. To be honest, I mean it's not that much. It's not that complex, but since I don't know how it works and I can't, you know, explain it on the spot, I don't know if there's much benefit in, you know, me breadboarding this out and trying this. I think, like, I mean, all you others, you have this in the chat now, so I guess you can check it out yourself. But I mean, if you're up for it, and you said, like some of you said that you are still up for it, I would like to show another design that I made that is really simple. And to be honest, I can't really tell you why it actually works. So maybe we can discuss it afterwards. So here is that circuit, and as you can see, it's, I don't know, I stumbled across this, and it was when I was still kind of a noob, and I didn't know what I was doing. And so basically what I thought, like my thoughts while kind of making this were, if you take this stuff here away, so if I just delete this, then what you have is just a simple inverting op-amp amplifier. So if I run this, then you can see that, oops, I have to bump up the speed to get it centered. Okay. So what you can see is you have your input signal here, which is properly loud. So I didn't need to scale it down. It's a 10 volts peak to peak input signal. Oops, my multimeter is complaining, sorry. Okay. So what I have here is a 10 volts peak to peak input signal, and I'm just feeding this into an op-amp set up in an inverting configuration. And what I've done is I've used a very big resistance here at the input, and I have used, I mean, this is essentially just, I mean, two 1K resistors in series is the same as one 2K resistor. And so what this is going to do is this is going to decrease the volume by a lot. So you can see that we are down to 10 millivolts or 20 millivolts peak to peak. And then I have AC coupling at the end. Very simple stuff. And now my idea was, and looking back, it's a stupid idea, and I don't know why I even tried this, but my basic idea was basically, what if I just take a transistor? I take just a basic, boring NPN transistor, like this, and I put that here. I connect the emitter to ground, because this is something that I did pick up, that you shouldn't, it never really work. Like when you're starting out, you're fantasizing about just using a transistor as a voltage controlled resistor, but it doesn't work, but it works even less if the emitter is not connected to ground. So I kind of, in the beginning, I figured out, okay, if I connect the emitter to ground, then it kind of, in some way, it kind of works like a voltage controlled resistor. So my reasoning was basically, or my idea was basically, what if I now apply a voltage to the base? And this, like in my naive conception, this would kind of open up the connection between collector and emitter. So then what happens, like it would open it up gradually. So with a rising voltage at the base, it would like gradually open up the connection between collector and emitter. And this would cause a current to flow, from this center point between these two resistors and into the resistor and to ground. And by that, you could kind of steal the current that the op amp is kind of pushing and pulling through here. And so in the end, you could make it just work harder to, like we saw earlier, to kind of balance the voltage between these 2 points. Because if you're sucking current away here, like it's kind of like a leak in the system. If you do that, then the op amp has to work harder. It should have to amplify, or it should in effect amplify the signal. And as you will see, or you might now say, like, if you know transistors, then the problem is this is going to, or this is how I understand it, it's going to push and pull current into and out of the transistor. And normally this should at least give you like this thumping, because like a transistor is not symmetrical, like it doesn't work the same way forwards as backwards. That's what I think now, and that's why I think it shouldn't work, or it should sound horrible. But as you will see now, if we take a voltage, a variable voltage, and we say, again, maximum is 12 volts, we should maybe push this up a little bit, and we will put it at 0 volts for now, and increase the speed of the simulation. And as you can see, this of course does nothing, because the transistor is not active, so we have the same situation as before. And you will already notice that this is actually, it's not loud, but there's still like an audible signal. 20 millivolts peak to peak is not nothing. You can definitely still hear this. You could probably make it quieter if you drop these resistances down even more, but I think that this created some problems with the transistor. But we will try it with one case for now and see what happens. So, okay, I will increase the voltage here. Okay, so 2 things. First of all, you can see that there is actually an increase in gain. So we are at, takes a really long time to center. Okay, so we are now at 2 volts peak to peak. A bit more than 2 volts peak to peak, like 2.2 volts peak to peak. And we're up from, what was it, like 10 millivolts peak to peak. So there is gain. But you can see that we have kind of a problem here, because we have a huge offset here. And curiously, you can see that it's kind of doing, it's not doing what I was expecting, or what I was naively expecting it to do. So all the current is kind of going into the base and coming out of the collector. So if anyone can explain this, or you know, like what this, why this, how this works, please enlighten us. What we can do if we want to get a bit more gain is we can drop this resistance down even more. We again have a lot of current going in here. You can see it's 11 milliamps, which is, I don't know if transistors, if this is healthy for the transistor, but like I explained earlier, this is a very noobish idea. But in effect, I mean, it kind of works. So now I've dropped the input voltage down to 0 volts again, and we're again at 10 millivolts peak to peak. So yeah, and now I'm asking you, should I build this? Should we listen to how this sounds, or are you not interested in hearing that? But first, let's check the rest of the comments. The transistor is hooked up to bleed off current, I think. So it will squash the peaks. That would imply that it's distorting the signal, right? We can try it in the simulation to put in a triangle wave and see what that looks like. The emitter is at a higher potential than the output of the BJT. That is why the current is flowing like that. Yes, because the collector is below ground voltage. Yes, but I'm wondering like why the op amp is going so far negative. But okay, you say try it out. I will just quickly breadboard it, and we will try it out. No, I mean what I meant is like why does the op amp get stuck like at this negative, at this like very very negative output? That's basically my question. But I mean, yeah, probably. I would have to look into it. Okay, so guys, I will build this and then we will kind of judge if this is any good. Like I still think that this design is much more refined and probably the better choice to build, but let's try it. Okay, enough breadboard. Get these out. Now the interesting thing is, I mean, we just need one single op amp, which is quite nice. I mean, in the end, like if this, I think in a pinch or like in some situations, maybe like you are building some other module that requires like some basic VCA stuff. Like I was thinking basically, for example, about like I want to do a spring tank driver soon. I was thinking about like making some of the parameters voltage controllable. So I would like to have like a brightness control, basically a filter like for the, or a bandpass filter for the driver. And it would be nice, you know, if that was, oh no, that's a filter. That's not what I meant. No, I meant the blend control, you know, so that you have a kind of a dry wet knob, but that you can also voltage control it so that you can like send in LFOs and stuff. I think that sounds very nice. And for that, maybe it's not that important that the VCA is like super precise or, you know, super sophisticated, but we'll see then. Okay, so let me try to set this up. So first we need power. This is the positive side, and this over here is going to be the negative side. 1, 2, 3, 4. Perfect. Okay, so I will just leave out the AC coupling for the input signal for now, because I know that my oscillator is AC coupled on the output anyway. So we can just drop this for now. Okay, so I will be using this op amp right here. We are going to use a 1 mega ohm resistor to send our input into the inverting, to send our oscillation to the inverting input. And we will also ground the non-inverting input. Okay, and now I'm lost. Ah no, now we need one case. I had a bag somewhere. But I seem to have misplaced them. Ah no, here they are. Okay, so we will need two 1K resistors. And how did this work? Ah, maybe we're going to move this over here. And then we have a bit more space to maneuver on this side of the breadboard. So we come from the inverting input. We go away with the 1K. And then we use another 1K to go back to the op-amp's output. Boom, put this in here. Right, and then from the output we just get our output signal. Who would have thought? And this time I don't have to do like a quick and dirty ugly connection. Instead I can just use this, and then I will put in a AC coupling cap for the output, because as we saw, the output is going to have quite a massive offset. So we want to control that by AC coupling the output. And I've recently discovered that, I mean, normally I use a 1 microfarad and a 100K resistor to ground to AC couple my signals, but I kind of discovered that this is kind of overkill, because if you calculate the cutoff frequency for that low pass, for that high pass, it's somewhere around like 1 hertz or even less, like 0.7 hertz. So I guess it's kind of over-dimensioned. So I could probably either use smaller caps or smaller resistors, and it should probably also help to center the signal quicker. But yeah, this is in. So let's get a jack socket. Just going to cannibalize this guy here. Sorry. Okay, so this will be our output. Okay, so the output is all done. And now all we need to do is we need to set up the transistor. And as you can see, this is really, really simple. I mean, it's just a handful of components. If you had a TLO71, you could probably like fit this on like this much of a breadboard. I have so many transistor types that I never use. Like I only use the BC548 and the BC558, and that's it. And all the others are just rotting away in their sad little drawer. It's really sad. Okay, here is the transistor, and I will, well, first we have to check out the pinout. So I think it's collector base emitter on these. So we want to connect the collector to our 1K resistors here. And we want to connect the emitter to ground. Okay, and then I need to jump the gap there. So we connect the collector to the intersection of the two 1Ks. Whoops. just really stubborn. Or I'm really clumsy, or both. Okay. And now I just need to send in our CV. Let's try it. I mean, like we saw earlier, my interface is actually kind of over-challenged with a loud input signal, so I'm just going to use a 2K for the CV input. I think this will give us 2 volts peak to peak in the end at the maximum setting. So this should be good enough for trying it out just now. Okay, and we need another jack socket. Put this guy in here. And that should be it. Connect the power lines. We also need to connect the ground lines here. I'm always happy when I catch stuff like that, like before I run into the problem, because oftentimes, you know, you spend just 5-10 minutes looking for a problem that is like so obvious that you just overlooked it in the first place. Okay, so positive goes here. They should make breadboards with like clearly, with 3 power rails. Like it's so annoying. Like I'm always so unsure, or I'm always paranoid that I might, plug something into the negative rail that should really be in the positive. Oh, I just saw that this is also one of those stupid like split rail breadboards. Everything is conspiring against me. This thing broke. Oh well. Okay, so again, I will use a triangle wave to send in, just so we can spot if there's distortions. And I think I have to disappoint you. I'm not sure if I'm going to bust out the oscilloscope today. Like, if you really want it, we can talk about it in a second. But for now, let's just see if this is any good, if this works. Whoops. I forgot to set up the input. Like right now, we only have the output and we have the CV input, but we don't have the actual audio input. So let's do that. I really need like a breakout board for the breadboard. Just something that has jack sockets and potentiometers and all that stuff, because this is really getting annoying. Okay, so I plugged my oscillator into the output. Great. Here, this is the output cable, and I will plug this into my interface. And interestingly, even though the power supply is not on, we can already hear something. Funky. So this is not powered, but we still get some VCA action. I don't know if you hear this. And interestingly, it's always on the down cycle of the LFO. So whenever the LFO right now goes negative, we get an output signal. Whatever. Okay, let's try to turn on the power supply. Okay, as you can hear, I would say it sounds very noisy. Like not distorted, but noisy, It has like this kind of airy, strange quality to it. try it with a different kind of waveform. Okay, I would say that's less noisy, but you can clearly hear that whenever the signal is in this low phase, you hear the signal still. I will turn down the LFO. Okay, so right now the LFO is not sending out anything, but you can still hear the signal very faintly. If I will now push up the input on the interface. I think you can hear it. So now the interface is about like 3 o'clock. So it's still considerably loud, I would say. So as we saw earlier, I think the only option that we would have here would be to decrease the value of these resistances or increase the value of this resistance. I don't have any resistors bigger than 1 mega ohm though. So what I will try to drop these down to. I mean, the problem is, like, even if I drop these down to 100 ohms, well, first of all, it's also going to be like a current grave. Let's go back to the simulation. We'll check the simulation and see, you know, how bad it would be if we did 100 ohms here. So let's see how much current we're wasting. We need to go down here. Well, okay, of course, at 0 volts we're not wasting anything. But what happens if we bump it up? Well, of course, it's also going to, like, very, very much dampen the maximum swing. So now we're only at 50 millivolts peak to peak. So this is clearly kind of unacceptable. I think that was the reason why I was using the one case here, because this gives us, as we see, this gives us like 5 volts peak to peak with a 2K, which we're using right now. We get what? We get about 2.2 volts peak to peak. So dropping these down is not really an option, I'm afraid. So yeah, let's check on the noise again, because that was a bit weird to me. It's really strange. Does anyone recognize this sort of noise? Is it maybe coming from the transistor itself? I think the problem is, I mean, like I explained earlier, I think if I really push my I'm using my LFO right now for the triangle wave. I think if I really push this up, then it goes up to like 20 volts peak to peak, and this might be the reason. Like if you really push a loud signal, into this, then it might just start distorting. But I think there's still some distortion there. Yep, definitely. No, I think it came from my interface actually. Yeah. Okay, that was my interface. Sorry. But I would still say it has like this very strange noisy kind of quality. Let's try it with my envelope. Okay, interesting. So this has like this extremely annoying clicking as well, even without an input signal. If I turn down the release, it gets even worse. Yeah. So I don't know about you guys, but I think that this kind of disqualifies this design. For me, at least. I mean, maybe you could kind of invest some time and effort to polish it up, but I'm not sure. Put 2 or more resistors in series to create more than 1 mega ohm. Yeah, I'm not sure if that actually solves our problem, actually. The transistor is providing an offset, not a control, I think. You've built a weird mixer with the inputs being the 400 hertz. Okay. Sometimes I also just think of them as 24 volts, 12 volts, 0 volts. But it's offset to one polarity. Yeah, I also think so. I mean, we see in the simulation that it's constantly stuck like in the negative spectrum on the output, or maybe like, you know, whenever it's jumping up, that probably causes some clicking. I'm not sure. Agree, trash it. Yeah, I would also say the previous design, which was much better. The transistor pumps an extremely nonlinear current into your op-amp circuit. Probably, yeah. Wouldn't the pop sound be the capacitor discharging? I don't really think so. Maybe. I mean, we saw that there is the problem with this offset. Maybe it just like it quickly changes from. If it quickly changes polarities, then that might explain the clicking. I'm not sure. Need an oscilloscope for debugging, sample it with a sound card. You know, guys, what I'm going to do is I'm going to also put this design in the description. I'm going to flag it as kind of like an incomplete or like a faulty circuit. And if you are so inclined, like if you're motivated, then you're very welcome to kind of try to you know, fix this, rework this, make this into something better. And if you can figure something out, then I'm very glad to give you the spotlight and you know, have you maybe present it on the circuit on the channel, something like that. But for now, I think I'm going to like, for me, I'm going to trash this circuit, because the one that I built earlier, I think it's just way nicer. Like the way that you can implement distortion, and the way that it's reacting to the CV, just all seems very promising to me. So, okay, so from my end, that will be all that I have. I don't have any more designs. If you have any questions, now would be the time to ask. Otherwise, I'm just going to start cleaning up a bit. I'm going to give you a bit of time to write something. If you don't have any questions, then I guess we're going to end this. But from my end, I've enjoyed this. I've also enjoyed coming up with a CV before, without looking up anything before, you know, without having something that I'm inspired by. I just used the diode ladder filter as the inspiration, and it turns out it works quite well. So I'm quite happy with that, actually. How about a Vectro VCA? You can definitely build a Vectro VCA very easily. The only problem that I have with Vectros is that they are not easy to control. Like they have their own like very weird kind of non-linearities, and you can compensate for that, but it will take a lot of work. So I mean, if you just need a quick and dirty VCA, or rather attenuator, you can definitely use a Vectro, but in most scenarios it's not going to be good enough, I think. It's just what I think. So how about that design I sent? I will have to look into it. Like I can't look at it on the spot and tell you what I think about it. I will look into it, and maybe next live stream we can talk about it as well. Shopping list, needle nose pliers. Oh, you mean these? Yeah, they're awesome. They came with my multimeter, and at first I got them out of the packaging, and I thought like, what am I going to do with this? And then in the end, I use it way more than the multimeter. So good thing that they were included. I think the problem might be bias related, but it's a cool idea. Yeah, it's a very naive idea. It's an interesting idea because I wouldn't have this idea nowadays, I think. But still, it's it's okay, I think. Planning for a follow-up stream. I've said this a few times already. I am trying to do a stream every Sunday from now on, except for when I'm busy with filming and editing for an episode. So you can expect there to be a live stream every weekend. I will try to cover like whatever just kind of occupies my mind at the moment. So, you know, this week it was VCAs. I have some other things on the list. Like I said, the spring tank driver circuit is one thing that I want to do. Wait, let me look up the list. I actually have a list of ideas. Oh yes, I want to do a triangle to sine wave converter. I want to do it like as simple as possible. Also, I would like to, now that we have a VCA, I would like to try to see if you can turn the VCA into a compressor. I have some ideas how that might work. Haven't tried it yet, so that might be interesting. And then one other thing that I would like to try, I'm really not sure if there's any merit to it, but I recently discovered like these, they're called varicaps. It's basically just diodes that you use as a voltage controlled capacitor. And they make these varicaps or these diodes in a very big form, so that they can, I think the maximum capacity that I saw was something like one nanofarad, something like that. And I think maybe you could use them to build a filter, but that's just speculation. So we will see about that. Nice session. Thanks a lot. Can't wait to get into envelopes with you. Yeah, envelopes, like I said, are going to be very soon, like a proper video on my channel. And thanks for watching. How often do you do these live streams? Like I said, I'm going to do them every Sunday from now on. No, these are tweezers. You need needle nose pliers to make your wire insertions. That's horrible. Ah, so it was a tip. Okay, I will look into it. Thank you. Follow-up stream means see your doctor. Yeah. Thanks a lot for the stream. Yeah, guys, thank you. Hope you got something out of it. Like I said, the stream will be available. On my Patreon. You will have access to the circuit simulations there in the description. I'm going to try and update the description, like whenever I make tweaks, whenever I add something, whenever I find something out that makes the circuits work better. So that's where you can find those things. Also, I have begun putting my PCB layouts on my Patreon. So the first one is up already. It's for the diode ladder filter. I've kind of refined the front plate a bit. I've refined the board itself. Component placement is kind of more friendly to solder because there were some things that are very close together. So I polished it up. It's out now. You can download it. You can send it to JLC. You can get it made, so you can get like, you know, my filter. Also, I have already like today I made a few improvements to the filter, which are very, very nice, and I think this will make it much more usable. So in the near future, you can also see you will also be able to find a Mark II version of the filter. I plan to do I plan to open like an online shop where you will be able to buy PCBs, front plates. You will also be able to buy kits. And if I get around to it, I will also assemble some modules for people that don't know or don't want to solder. This will be coming up very soon. Varicaps have their capacitance very nonlinear. Yeah, that's what I feared. But I still want to just try it, you know, just see what it sounds like. Maybe it's interesting. The popping is the massive offset introduced by the CV along with the amplification. Yeah, probably. Love your show. Thanks for sharing. Thank you, Eric. Thanks for watching. Thanks, James. Thanks, Roland. Thanks, everyone else. Hope you have a nice night, and talk to you soon. Bye-bye, guys.